So as we've found out about other planetary systems, we've actually found some things that have made us question or at least reconsider the nebular theory. So if you remember, the nebular theory is the idea or our current understanding of how it is our solar system formed. But there are some things that we've discovered that don't fit nicely into the nebular theory. For example, according to the nebular theory, Jovian planets should form far away from the star, beyond the frost line where the solar system is cold. And yet we have found hot Jupiters, Jovian planets that are really close into their star. Something else that we have predicted from the nebular theory is the idea that planets should have nearly circular orbits, and yet we have found many planets with very eccentric orbits, very, very large eccentricities. In fact, we found a planet that actually crosses through the habitable zone. So it starts out too cold, goes through the habitable zone, gets too hot, goes back through the habitable zone, out back to where it's too cold. If you don't know the habitable zone, we'll discuss it in just a little bit. Okay, so we have to be able to still explain some of these things. Now, we still think the nebular theory is the right idea, but we have had to modify it. So one of the things that we've had to do is to try and explain hot Jupiters. Well, as we have tried to figure out how this could fit in the nebular theory, we have done computer simulations. And one of the things that we see from these computer simulations is that planets don't actually have to stay where they began forming. In fact, it is likely that planets are able to move around. So, for example, we can have a forming Jovian planet, and as it forms, its gravity is going to possibly create knots and ripples within the protoplanetary disk around it, which will then have a gravitational influence, which can then draw the planet closer into the sun, creating a hot Jupiter. We've also seen that it may be possible to actually pull a Jovian planet out farther away than where it began to form. This is the process of planetary migration. Okay, so again, this is planetary migration. And in fact, we actually have evidence that Jupiter isn't where it actually began forming, that for a period it actually moved in closer towards the sun, disrupting the asteroid belt, leading to what is referred to as the period of heavy bombardment. We then believe that it's also been pulled back out farther away from the sun, in this case because of Saturn's gravitational influence. Now, planets with highly eccentric orbits may be caused by two possible things. First, we may have a gravitational encounter. So what happens during a gravitational encounter is we may have two planets on orbits that are very close to each other. Well, as these two planets are orbiting around, it is possible that they get so close together that they exchange a lot of orbital energy. What happens in that case is the planet that steals the orbital energy will actually get ejected out away from the solar system. It will get thrown out into interplanetary space. It will literally be lost. Then the planet that remains, that had all of that energy stolen, is now thrown on a wildly eccentric orbit. So this is one possibility, is due to a gravitational encounter. Another possibility is orbital resonance. We mentioned this previously when talking about Jupiter and the asteroid belt. The idea of an orbital resonance is that we have multiple objects, two or more, whose orbits are even integers of each other. Okay, so a great place to actually see this are three of the moons of Jupiter, Io, Europa, and Ganymede. Every time that Ganymede has orbited exactly one time, Europa has orbited exactly 2 times, and Io has orbited exactly 4 times. So what this means is they keep lining up in the exact same place within their orbit. Because they line up in the same place, they keep having a gravitational tug on them in the same place in their orbit, which is then going to shift and tweak the size and shape of their orbit. If we have multiple planets doing the exact same thing around the sun, we could see highly elongated orbits because of these orbital resonances. So that's another possibility. All right, here's another question. How have we modified the nebular theory to account for hot Jupiters? A. Planets are allowed to move from where they began to form due to gravitational interactions. B. We have had to account for frost line variability, allowing the frost line to move during planet formation. Or C. We have not had to modify the nebular theory at all. Go ahead and think about it, and we'll discuss in just a bit. All right, so the way that we've had to modify the nebular theory is the idea of planets moving. Planets are allowed to move. Planets don't actually have to stay where they began forming. Due to gravitational encounters, they can get pulled in closer to the star or get moved out farther away from the star. So the correct answer is A. Now, we still have other possibilities, other things that we're going to need to explain with the nebular theory. As we've found other planetary systems, we've actually found other types of planets than just the terrestrial and Jovian that we have in our own solar system. Some of these we can still explain pretty easily using the nebular theory. For example, there are some planets which are referred to as water worlds. These are planets that are slightly larger than terrestrial planets, but they're much smaller than the Jovian planets in our own solar system. These planets, based off of their density, are going to be made of primarily water and then likely have a small rocky core down at the center. So these are water worlds. They are made of mostly water. Now, with these water worlds, we think that they may have actually begun forming like a Jovian planet. So they were out beyond the frost line where we had rock, metal, and ices. And they began to form through condensation and accretion. However, in our own solar system, after these cores of rock, metal, and ice got large enough, they were then able to start pulling in a lot of hydrogen and helium gas. What we think happened with these water worlds is that these planet formation ended before these planets were large enough and had opportunity to start pulling in a lot of hydrogen and helium gas, which means that they're left as the rocky, icy objects that they started as. Now, although we have some idea able to explain some of these, there are other of these new types of planets that we're still struggling with. For example, there are what are referred to as super-Earths. A super-Earth is a terrestrial planet that is even larger than the Earth. We have found some of these that have a radius as much as 2.5 times the radius of the Earth. So they're getting pretty big. And yet, they have to be pretty much terrestrial, made of just rock and metal. So how is it that you can get that much rock and metal all in one place to create a super-Earth? This is still an ongoing question. Similarly, based off of densities, we've found some terrestrial-like planets, but with very, very little rock. They have to be made of almost pure metal based off of the densities that we're seeing. So how is it that you can get a planet that size that's just metal? We still have a lot of questions that we need to answer, but overall it still does look like the nebular theory is going to be able to do it. We just need to find tweaks and modifications. Now, the ultimate question we have is our own solar system common? Or do we find other solar systems with Jovian planets far out and terrestrial planets close in? And unfortunately, we just don't know. As we've looked at, we've found a lot of planets. We found hot Jupiters. We found super-Earths. Neither of those are actually found in our own solar system. However, a lot of our data, remember, where most of our data is coming from the Doppler shift method and the transit method, both of which are only looking at planets that are very close into their star. And so because of that, we actually don't know. This is an ongoing question. Over the next several years and decades, as we get better and better with our techniques and possibly even come up with more and different techniques of finding extrasolar planets, then we'll probably be able to figure out, is our planetary system common or not?